make sure you have units with your answer. Okay, so the first part of this problem looks almost identical to the last one that we did. The only thing that's different is that what you're given is a little bit different. Your radius is given as 4 this time. They give you dRdt is 1. So the radius is increasing at a constant rate this time, and they're solving for dAdt. So the derivative is the exact same as it was for the last problem. You're going to plug in all of those values. So r is 4, dRdt is 1. You should get 8 pi. What are your units in this scenario? It is feet squared per, feet squared per second. Because A stands for area. Area is measured in square units. So it's feet squared, and then T is time, that is seconds. So your area is increasing at a rate of 8 pi per second. Now let's think about this scenario, because it's a little bit different. Your radius is increasing at a constant rate. So your radius is getting 1 foot bigger each second. What's happening to your area? It's increasing, but how? Is it increasing slowly at first and then very fast at the end? Or is the area increasing very fast at first and then slowly at the end? So your radius starts off like a circle with a radius of 1 just has an area of pi, right? And then a second later it would be 2. So that'd be 4 pi. And then the next one would be 9 pi. And then 16 pi. And then 25 pi. Actually, I'm missing a 2. No, that's the rate. So that's correct. So it starts off pretty small, but then it gets big kind of fast, right, as those numbers get larger and larger. So this would sort of be the opposite of the scenario we had earlier. And earlier when the area is increasing at a constant rate, the radius starts off growing fast and then slower. When your radius is increasing at a rate, you start off area is very small, and then it starts to grow much faster after that. So those are kind of interesting to think about. Okay, let's go 3D now. So let's start talking about volume. So for example 3, air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Describe how the length of the radius of the balloon changes as the air is pumped into the balloon. And then B says find the rate of change of the radius when the radius is 2. So A first asked me to think about the balloon. And I meant to bring a balloon, but I didn't. So imagine, probably everybody's blown up a balloon before, right? So imagine blowing up a balloon, and you blow up a balloon, like you start off, it's just flat, you blow like 1 breath, let's just say a breath at a time, 1 breath in, and it's going to blow up the balloon some. And then you got a second breath, and a third breath, and a fourth breath to blow up that balloon. How is the radius changing as the air is pumped into that balloon? Does it grow quickly at first and then more slowly, or is it the opposite? So at first, like that first, it goes from nothing to poof, you got a balloon, right? But those like last few breaths, you'll blow and it just gets a little bit bigger, right? So the radius increases quickly at first, and then more slowly. Let's say that in a little bit more mathematical way. First of all, the radius is increasing the whole time, right? So we could say the radius increases Okay, and it's fast at first and then more slowly. So the rate of change of the radius, is it increasing or decreasing? Decreasing. So it increases at a decreasing rate. And that means that it would be like concave down, right? It would start off getting bigger pretty fast, and then it sort of slows down. But it's still increasing the whole time. So that's just asking you to think about it a little bit. B is actually asking you to do a problem, right? So first of all, we are going to need our formula. What formula would we use for a spherical balloon? Anybody remember volume of a sphere? That one is 4/3 pi r cubed. They usually give you that in the problem. They'll usually give that to you in the problem. So I will give it to you in the problem on a quiz or a test. So the textbook probably does not, but the textbook does have a lot of area and volume formulas. Either in that front cover or back cover, it's got them there, or you can Google them for that. So this is volume of a sphere. We must identify variables that are changing, constant, and what we're solving for. So in this case, when we're blowing up the balloon, is the volume changing? Yes, right. Is the radius changing? Yes. So for changing, we've got volume and radius. For constant, I believe they give us something constant there. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. It doesn't say constant, but I'm pretty sure that's what it means by that. It doesn't tell you it's changing. So what is the air is pumped into the balloon at a rate of 4.5 cubic inches per minute. Which one's that one going to be? It's a rate, so it's one of the DTs. It's dV dt. So dV dt is 4.5 cubic inches per minute. And if you're not sure about what it's talking about, because it just says air pumped in, it doesn't talk about the volume, the units can help you a lot on that. It's cubic inches. Cubic inches are used to measure volume, so that tells you it's dV dt and not dr dt for that. And we're supposed to find the rate of change of the radius. Rate of change of the radius, what is that? What variable would that be? Dr dt. So we are going to solve for dr dt. And we are specifically looking at the instant where r equals 2. So I'm going to put this over here, that r equals 2. But can I plug this in before I take the derivative? I cannot, because that value is changing. It's in my changing section. We're going to see one in a second, I promise, where it goes in the constant section and we can plug it in. But that's not going to be the case here. So we can't plug in any constants. We don't need to convert it to one variable because this also still just has two variables in it, so it's not going to be necessary. So we need to take the derivative. So the derivative of v is just dv dt. We've got 4/3 pi r cubed. 4/3 pi doesn't necessarily look like it, but it's just a constant. So you're just doing the power rule here. So you're going to be doing like that 4/3 pi times the 3, and then the r will be to the second power. That 3 is like 3 over 1, so it's going to cancel with that 3 in the bottom, and you will just get 4 pi r squared, except for I'm forgetting something. What do I need? Dr dt should be here. Let me just write it over here prettier. dv dt equals 4 pi r squared dr dt. Everybody good here? If you can get here and you have already identified this stuff, you are usually pretty good. You just have to plug those numbers in. So R is 2, dV dt is 4.5. So we'll plug in 4.5 right here. We got 4 pi 2 squared dr dt. And so 2 squared is 4 times that 4 right there gives us 16 pi and then we'll divide by that 16 pi. And I'm going to go ahead and just use the calculator on that because I don't like decimals inside of fractions. And I'm getting 0.0895 as my dr dt. In any problem where they give you units, which the word problems are almost always going to have units, the problems like yesterday won't because they're just naked problems with no scenario. These will almost always have units, so I want units on the answer. A lot of times this will be on the free response and they'll ask for the units. What are our units for this problem? Not quite. It's not cubic inches. It's just inches. Because if you look at like what the variable you're solving for, look at what if dr is like change in r and dt is like change in t. So r would just be measured in inches for that. So it would be inches per minute. If it were dv dt, it would be cubic inches per minute. Okay, questions? All right, let's keep moving. Oh, I have a mistake on this right here. That should not say right circular cone. It should say right circular cylinder. Fix that on example 4, because clearly I did not mean for it to be a cone, because I've got a picture of a cylinder over here. Okay, so there's a good chance you run into a tank problem of some sort, or something similar to a tank problem. And once again, I'd love to call in somebody that works somewhere to tell us about these giant industrial tanks that they have to deal with that they do this, but I don't personally know anybody who does that. So, if we have a tank, and this tank has a radius of 8 meters, and it has a height of 10 meters. It is being drained at a rate of 50 cubic meters per hour. At what rate is the height of the water level changing? Now, these can be a little bit tricky because they have some information you really don't need for this. So we got water in this tank. Is the tank full? We don't really know. It didn't tell us, right? It might have been full whenever it started. We do know it's being drained, so it's not full the whole time, right? So what's happening is as it drains, our water level is dropping, right? So that water level, which I'm going to call H right here, is actually the height of the amount of water in the tank. Is the height of the water ever 10? Only one time whenever it's 100% full, and we don't even know if it starts off being full, right? So this 10 right here, you actually do not use at all. It's information you have. You do not need to use it in the problem at all. Because what the problem's asking you about is the amount of water in the tank, not how much the tank itself holds. So, question for you here, though. The height, well, let's go ahead. I'm going to do formula first. You might remember volume formula for a cylinder. It is volume is pi r squared. What's pi r squared? Area of a circle. It's the area of the base of this, right? And then you multiply it by the height. Okay. They usually give that one to you. If I was feeling a little iffy, like maybe that one, if it's a cone or a sphere, they definitely usually give it to you. Maybe they'd want you to know this one. It wouldn't hurt to know that one, but I'll give it to you if I give you one of these problems on a quiz or a test. In this case, we got to think about variables that are changing or constant. So let's thinking about changing. Actually, I'm going to go ahead and do changing and constant here. So I'm going to walk through the variables in the problem first. Volume. Is our volume of the water in the tank changing? Yes. So volume is changing. Pi is a constant. We don't use it. Is the radius changing? The radius is not changing. That water level is dropping, but the sides of this are straight. Radius stays the same. So here's an example where our radius can go over here as a constant value. We haven't had that happen yet. We haven't had any like just single variable go in the constant section yet. What about height? Is height changing or is it constant? It is changing, so it goes over here. Okay, we also want to think about rates, because if we have these rates, like if we have, it's going to give us some rates. So it tells us the tank is being drained at a rate of 50 cubic meters per hour. They don't use the word constant there, but you would imply that it is constant. So what is that? What variable? It's definitely going to be a dt of some sort. It's dv dt. And it is constant, so dv dt is 50. And actually, we've got to be careful here. It really is not 50. Because is that volume increasing or decreasing? It is negative 50 cubic meters per hour. So sometimes they don't give you the sign there, but if the amount is decreasing, you need to make that rate negative. Okay. They don't give us any other rates. What are we asked to solve for? The rate that the height of the water is changing. What variable would that be? dH dt. The only thing I don't see is a dr dt, but we're going to find out we don't actually have to have a dr dt for this problem, because r is over here in the constant section. So we haven't done this step 3 yet because we haven't had any problems where we needed to do it. But if I have any variables that show up in the constant section over here, I can plug them in before I take the derivative because they never change, right? So they're the same before or after the derivative. So I can take r equals 8 right here and plug it in to my equation before I take the derivative. This only works if it's a constant value. We couldn't do it on the other problems so far. So we'll have v equals pi times 8 squared times height, and it will make your life a little bit easier to clean that up just a little bit. Volume equals 64 pi times height. Now, if I still had r in the equation, I might need to do a step 4 where I got it down to like 2 variables, but my equation now only has a v and an h, so unlikely that I'll need to change that. So I'm going to take the derivative. So derivative of v is dv dt. And then what's the derivative of 64 pi times h? 64 pi. And we got to put a dh dt with it. notice this problem, like most of the other problems have said like when the height is 7, what is the rate of change of something? Or when the radius is this, what's the... this problem does not do that. But it doesn't have to, because do we have any straight variables from the problem even left here? All we have are rates of change, right? So it doesn't have to say what is the rate of change when the height is 7, because there is no h to plug in here. So what is happening here is dv dt and dh dt are not the same, but they are both going to be constant. And if you think of that, it makes sense, because as this drains, like if we're taking the water out at a constant rate, the height's going to drop at a constant rate here. So we just need to plug in that 50 for our dv dt. So we got 50 is dv dt. We got 60 for, oh, I'm sorry, yes, negative 50. dh dt. And we will divide both sides by 64 pi. And let's use the calculator to get an approximation for that. And I'm getting dh dt is going to equal negative 0.24. Let's go 249. Round that off a little bit. What would the units on this one be? Meters per hour. Very good. Because height is what our H stands for. Height could be measured in meters. T is time. That would be hour. Yes?
I did the negative 50 over 64 pi, and I got negative 2.4.
I think you need to have 64 pi in parentheses. I think yours is doing negative 50 divided by 64 and then multiplying that fraction by pi.
Yeah, that was it.
Yeah. Okay, questions? All right. Okay, we got 2 more to go. We're going to make it. Definitely, maybe a little time to spare. Maybe time to go over that FRQ. All right, so a block of ice is in the shape of a square prism. The original dimensions of the block of ice are 4 by 4 by 8. As the ice cube melts, I really shouldn't have called it a cube. I should have called it a prism. It's not a cube. Let's just say as the ice melts. It retains the property that its height is twice the length of one side of its square base. If x is decreasing at a constant rate of 0.1 feet per hour, at what rate is the volume of the ice cube decreasing when x equals 0.5? Okay, so this one's got a lot going on here. So they give us that the original block of ice is 4 by 4 by 8. But does it stay 4 by 4 by 8? It melts, right? And it retains like the same properties, like it's the same shape. It's just like shrinking, right? So does the base stay 4 by 4? It's not. It's going to get smaller, and the height does not stay 8. It gets smaller. So everything's changing here. Your 4 by 4 by 8 is not used in the problem. It's just extra information that you'll have here. So the way I would do this problem, I would probably call like this side right here x. This would also be x because it tells you it is a square prism, which means the base is a square. And then the height is different over here. So if we're looking at the volume of this prism, we would have volume equals x times h. Just length times width times height. You would probably want to write that as x squared times h. So, let's see. We need to identify what's constant, what's changing, and what they're asking us to solve for. So, constant, well, let's do changing first. I'm doing changing first. Changing constant solvable. Alright, so, is volume changing? Yes. Is X changing? Yes, because it's shrinking. Is H changing? Yes, because the whole thing's just shrinking. Alright, so all of your variables, all of your main variables are changing. The only thing that we have constant that we know is it does tell us X is decreasing at a constant rate of 0.1. What variable would that be? Dx dt. And since it is decreasing, we want to use negative 0.1. And that is feet per hour. And typically your solve for is going to be like your last sentence. It says, at what rate is the volume of the ice cube decreasing when x equals 0.5? So what variable are we solving for? dv dt, because it asks at what rate is the volume changing. So rate of the volume would be dv dt. They do give us this piece of information over here, that x equals 0.5. That is going to be necessary to use, but we cannot plug it in before we take the derivative because it's in our changing category, not our constant category. So we will not do step 3 for this because the only thing we have that is constant is a rate, and that's not going to show up until after we take the derivative. But this problem is going to require us to convert to a single variable here. Or, well, I guess it's 2 variables. Because I'm going to do this, don't do it, okay? Because it's going to take up too much room and there's already not a lot of space there. I'm going to erase it in a second. If I use this equation, I've got x squared h. If I take that derivative, I get dv dt equals, and I have to use product rule right here. So that would be x squared times dh dt plus h times 2x dx dt. Here's what, sometimes that works if they've given you a lot of information. But if we think about what we could plug in, I know what x is, so I could plug in for those x's. I know what dx dt is, so I could plug in for that. I'm solving for dv dt, so that would be fine. I could figure out h pretty easily because the height is always twice the x. But do I know anything about the h dt? I do not. I might could reason through what it would be for this scenario, but in my mind, I think it would be just a lot easier to change the original equation for this. Because I can't do anything with that dh dt, so I'm going to hit a roadblock if I don't do this next step. In this right here, they told us that this retains its property that its height is twice the length of one of the sides of its square base. So the height is 2x, right? So if I go back and I decide maybe instead of h, I'm going to call this 2 times x. That should still give me the same shape, right? So if that's the case, that means that we don't want to do this, but we want to do v equals x squared times 2x. So instead of height, we were going to use 2x. And that would mean volume equals 2x cubed. It's just a lot easier to do this before you convert. And if you can, you want to get it to fewer variables before you start plugging in. It just makes it easier to solve the problem. This usually does not happen on like everything we've seen so far where we only had 2 variables anyway, but if you have 3 or more variables, sometimes it is an option. So once we get to here, we're just doing the same thing we've done for the other problems. We're going to get dv dt equals 6x squared dx dt when we take that derivative. And then we just need to look back up to our step 2, plug in our pieces of information that we had. The VDT is what we're solving for. We do not replace it. We got x is 0.5 and dx dt is negative 0.1. And I'm just going to plug that stuff into the calculator. And I'm getting that dv dt is negative 0.1. And so, what are the units for that for dv dt? Cubic feet per hour. I would say on this one it could go either way. The calculator doesn't really help you much because really the only thing you're really going to be able to do on the calculator is the last step. So they might put it on the calculator active just because it doesn't help you that much to have it. Or they might expect you to do these calculations without the calculator. So I could say this one could probably be on either section. When you're doing your homework, I would do either way. If it's pretty simple, then you could just leave it as a fraction or something. If this was a free response question, you could always just stop here. You wouldn't have to get the final answer. So it could really be either way. Okay, questions? All right, we have worked our way up to the cone problem. The cone problems are the most difficult of these. And that is because here we've got a conical tank that is being drained. The water level, it's being drained at a rate of 3 cubic feet per minute. Now, in the cone, as you drain water from that cone, you're going to think the water level is going to be dropping, right? So as you drain this cone, definitely the height of the water is decreasing, right? What about the radius of the water? It's also changing, right? So that's what makes this a lot more difficult than the cylinder. In the cylinder, the radius did not change, so we could plug it in before we took the derivative. In this case, your radius and your height are changing whenever you do this problem. So volume of a cone is going to be 1/3 of a cylinder. I don't know if I ever did that. I didn't have you guys in Math 3, but I always do it in Math 3, like I have a cone and a cylinder that have the same radius and the same height, and I always have them guess how many cones it takes to fill up a cylinder. I don't know if you guys have ever seen anybody do that. Kids almost never guess that it takes 3 of the cones, but it does. It takes 3 cones to fill up one cylinder that is the same height. So your formula is just 1/3 times the area of a cylinder, which we just did was power squared times height. And so we really already talked about our changing and our constant. Changing, these are the hardest ones because all your variables are changing. V, R, and H are all changing. constant for this is our rate that the water is being drained is 3 cubic feet per minute. What is that? What variable would we have for that? It is dV dt. And the units can help you a lot on that. It's cubic feet, so it's got to be volume because it's cubic. And then we're going to solve for how fast is the water level dropping? That's dH dt. And they tell us that we're looking for when the water level is 6. So we can't plug it in before we take the derivative, but h equals 6 is the spot that we're looking at. And I should put that constant would be -3 cubic feet per minute. We actually do on this one. It's a little different. Now, certainly the height does not stay 14. The reason that we need it for this problem is because on the other problem, we knew like that height was twice the base. We knew what the relationship between those things. Do they give us anything that tells us like our relationship between our radius and our height? They do not, right? They don't tell us like the radius is half of the height or anything like that. So what happens for this is this original cone has a height of 14 and a radius of 5. Oh, I should have labeled that 5. There, not R. The water, we're just going to say it has a radius of R because we don't know what it is at every point because it's changing. And then we've got a height of H. So notice that I know this H, I'm looking for the H dt. It gives me dV dt. Do we have any information about R? We do not have any information about R. If I take the derivative of this as it is right now, I'm going to get a dr dt somewhere in there. But I don't know dr dt. And if there's a way to find dr dt, it's going to be difficult. I don't really know how to do it. So I would really like to get rid of the R in this equation. And then I'll make it much easier to do the problem. So what happens right here with this cone? As our water drains from our cone, the small cone, which is the water, is similar to the bigger cone, right? This angle right here is going to stay the same. That you're going to have a proportional relationship. So it would have to be true in this case that our radius, switch back to the pen, our radius over our height would have to equal 5 over 14. So radius divided by height always has to give you the same proportion as 5 divided by 14. This piece of information we can use to convert our equation. So we really don't want to have an R in the equation, right? We want to get rid of the R. So that means we need to solve this equation for R, and then we can plug that into our other equation. So how would I solve that equation for R? We can't plug in yet because we have not taken the derivative yet. So we wouldn't want to do that yet. So we'll have to multiply by H here. So R equals 5/14 times H. So we are going to take this and plug it in for the R in our equation. These are a little messier than the other problems that we've done so far, but if you're just careful with it, it's still similar to what we're doing. So we got 1/3 pi, and then we got 5 over 14 h squared times h. Technically, you've done it here. You can go ahead and take the derivative from this, but it'll be easier if you clean it up a little bit. So I would make everything fractions, at least in this first part. I would write this as 1/3 and pi. I could write it as pi divided by 3. When I square this 5 over 14, I'm just squaring the top, squaring the bottom. So when I square 5, I'm going to get 25. 14 squared, is that 169, 196, 196. And then I'll have an h squared, and I also have this h over here. So it's kind of ugly, but you got like volume equals 25 pi over, oh gosh, 3 times 196. This is like these are definitely okay if you use the calculator on them. 588, and then h squared times h will give me h to the 3rd. Kind of ugly, but we do have it down to a pretty simple equation there, because this is 25 pi over 588. As ugly as it is, it's still just a number, right? So this is just a power rule sort of problem. So now that everything's one variable, we're going to take our derivative. So I got dv dt equals, we're going to have to do 25 pi over 588, and then we're going to do 3h squared dh dt. It's up to you whether you want to switch to decimals, stick with fractions here. This is definitely one I'd let you use your calculator on. This dv dt. I might just go ahead and do a big decimal for that, because I'm going to want a decimal in the end. I'm getting 0.40071 h squared dh dt. Questions? All right. So if you get here, you're about there. You just need to plug in your information way back up here. H is 6. dv dt is -3. So we got -3 equals 0.40071 times 6 squared dh dt. Let's multiply that stuff together there. We'll get -3 equals 14.42568 dh dt. I just typed this stuff here in the calculator. You're going to divide that off. And -3 divided by that number is going to give us -0.20796, and so on. And that's going to be our dh dt. What would units be on this one? Almost. Just feet. Because height would just be feet. If it was dv dt, it would be feet cubed. So it would be feet per minute. Now, those are pretty much the worst you're going to get on volume problem. I mean, it can be worse, I think that's the worst you're going to see that I'm going to give you, and hopefully the worst you're going to see on the exam. It can get worse if you have crazier shapes than this, but these are ones you normally see. Your assignment is it's from the textbook. It is page 1. It starts on 194, but I think it actually goes on to several pages, so you probably need to look at your book and take pictures. 14 through 18 and 44 through 46. I printed your notes before I decided to add this bonus problem here. So it is like the notes that are posted to Canvas have it on the end of it if you don't want to like try to write that down or anything. So